This is geometry lesson 3.2, rotations. All right, our big idea says every rotation has a point that is fixed, that is its center, and a magnitude, either positive or negative, that is the measure of an arc, clockwise and counterclockwise. So we talked about arcs in our last lesson. We talked about angles and degrees, and we're going to use those now to rotate figures around a center. So a rotation is just the mathematical model for a turn. So you have a center and you've got some kind of figure, and that figure is going to spin around it. And so that center actually stays where it's at, and we rotate those figures around the center one way or the other. And so they end up on the other side somewhere like this, a certain number of degrees. Now the center could be in the middle of that shape, and that shape will just spin, but very often the center that we're rotating around is some point out here, and that shape will rotate around or orbit around as if you studied the planets orbiting the sun. Now, we're going to give those a degree measurement. How much did it rotate? How much of a rotation? And we have to call one direction positive and one direction negative, and it's a little counterintuitive. You would think clockwise might be positive, but it's actually the opposite. So counterclockwise, the way I've got this going, if you think about a clock, the way the hands go, that's going to be the negative direction. Counterclockwise is your positive direction. So if we see it going across the top of the circle from right to left, that's counterclockwise. So that would be a positive rotation. Okay, example number 1. Figure at the right, we have the dashed ray, OH. You notice it right here. That represents the direction the fox is facing. So we've got the fox at O. It's looking this direction towards H. If the fox's field of vision is 85 degrees. So we've kind of got a lot of arcs going on here. I want to make sure we understand what each one is. That's 85 degrees. They're calling that the field of vision, meaning the fox is looking this way and it can see this far. Okay, because its field of vision lets it see a little to the left, a little to the right without turning its head. So how much of a turn is necessary so that the fox can see something directly behind it? So if this whole thing is 85 degrees, we can split it into two pieces. This ray, OH, is splitting the 85 into two pieces, and you can see it right here. It's 42.5. That means this over here is also 42.5, and if you add those together, you'll get 85. And so what I want to focus on here is half of the circle. So let's just look here at the bottom half. If I've got this fox looking directly this way, I want to know how many degrees does he need to turn his head so that he can see here. Now it would be 180 degrees if we wanted the center of what he's looking at to face this way. But when his head is facing directly towards H, he's not just seeing H. He can see a little this way, he can see a little this way. And so what we want to figure out is how many degrees does he need to turn his head so that this X ends up here. And you'll notice that we've got another X over here with this little marking. We'll talk about that in a second, what that means. But to highlight it in, all of this is what he currently sees. So we just need to turn his head enough so that this part is here. And they've already got all the lines set up for you. This would be his new H, where his head is facing, and he would be able to see all of this. So how many degrees of a turn is that? So we know from here to here is 180 degrees, half the circle. We also know that this part right here, I covered it up so I'll rewrite it, is 42.5. So we're already 42.5 of the way towards where we need to get to. We just need to get the rest of the way there. So if we're going from H all the way to X, it'd be 180, but we're doing 42.5 less than that. So we're going to go ahead and take 180, and we're going to minus the 42.5 that our field of vision already covers. And that's going to leave us with the rest of this. which would be 137.5 degrees. You can always double check yourself. Take your 137.5 and add 42.5, and there's your 180, which covers half the circle. So this piece and this piece, if you think of it like a pizza, have to add up to 180. We've already got the 42.5, so you take 180 minus 42.5, and that leaves you with this. So to answer the question, how many degrees would he need to turn his head so that his field of vision would now cover this? It would be 137.5 degrees. Okay, now this is called your magnitude. We're getting to this right here. That's the measurement of the amount of rotation, and that's going to be in degrees. Now, we also talked about positives and negatives here. Now, it didn't ask specifically the magnitude of the rotation. If it was asking you like that, we'd have to think positive and negative. This just says how much of a turn is necessary. But to keep things consistent here with how we're going to speak about these rotations, we do want to consider the positive and the negative. And so if you look at the turn that we've made here, that is going clockwise. So like we talked about, that's a negative direction. So it is going to be a negative 137.5 degree turn, because if we set a positive 135 degree turn, we would be going this way. And if now he could get there, right? His field of vision is all the way over here at F. So if he turned his head this way, it's also 42.5 over here. So a positive 137.5 degree turn would get him there, just going the other way. So it would be either answer here, just depending on which direction you're turning. So he could turn 137.5 degrees this way, or negative 137.5 degrees this way. Now we talked about these little markings. We have an X, and then we have this X with this little thing here. That's going to mark our pre-image and our image. And we call that prime. So this is X prime, and this is just X. Or you can call this the image of X. Okay, so the pre-image is your original figure. Pre meaning that's what it was at the beginning. Pre-image. Okay, and then the image is the new figure after some kind of transformation. So today we're talking about rotations. But we'll be looking at other types of transformations as well, and we'll still be considering the pre-image and the image. So in this case, we're talking about rotations, though. That's a transformation. So some kind of movement for our image. So this is the image of X, and that's the pre-image, the original and the new one. And again, the magnitude, that's the degrees that measures how much of a turn was made. So if we look down here at the bottom, pentagon, and then with all the markings, P-E-N-T-A, is the image of, meaning it's the new version of the pre-image, penta, under rotation about the center G. What's the magnitude of the rotation? So this was the original shape, and it rotated around G. It's spinning around that. If you do these by hand, which we're not going to do today, but if you were rotating these by hand, you kind of need some tracing paper. And what you do is you trace the pre-image and you hold your finger down on G and you spin the tracing paper around, and that will show you where the new one is. Because you can see that you might think it should end up the same distance away from G, but as this shape turns like this, the shape actually rotates a little bit. And so it's a little tricky. You can't just measure a distance and put it on the other side. So tracing paper is really needed if you're going to physically rotate these things. But we're just looking at how many degrees was here. And so we're going to go ahead and grab a protractor and simply just measure how many degrees this turned. I'll get that upside down. So you're going to put the little circle here at the bottom right on the angle and follow this out. We're going to estimate here, depending on your line. It's going to be close. Looks like about 65 degrees. And then we do need to consider positives and negatives. This went clockwise. So this is negative 65 degrees. All right, let's flip it over. look at this a little differently here. So some of you may be in band and you may know some things about music and some chords. You may just play the guitar and know things about chords or the piano. When 12 different possible notes are placed on a circle as shown at the right, the notes of a C major chord are represented by the vertices of the triangle CEG. So if you're not musical and you haven't studied this stuff, it's okay. We just need to know that we've got C, E, and G at the vertices of this triangle. And we're going to talk about spinning that triangle inside the circle or rotating it. So to find the notes of other major chords, you can rotate the triangle clockwise. Okay, clockwise, this way, about the center O of the circle. Okay, so what you need to notice here is this is a C major chord, and we have C, E, and G. So this is the vertice that's naming this. This is the C major. So if we're going to try and get to a D sharp major, we find it right here. We've got to spin this, and again, we're going clockwise. This C needs to end up right here at the D sharp. So if you kind of just, these are all equal arcs. This is 1, 2, 3. The triangle is spinning 3 spots clockwise. Okay, so we're going to name the notes of a D sharp major chord. So obviously D sharp is the first one. This vertice that was on E also has to move the same amount as C did. So again, C went 1, 2, 3. So E is going to go 1, 2, 3, which means I'm going to have a G. And this G is going to go 1, 2, 3. That's going to put me at A sharp. If we wanted to, we could draw the new circle, the new triangle. So the D is going to go up to G, and then it's going to go over to A sharp, and then it's going to go down. Okay, so what we did was we started with CEG. We figured out, okay, it's named by the first letter here. This is a C major chord. If we're going to get to a D sharp major chord, we're going to rotate this triangle, figure out how many arcs it's rotating. If we wanted to, we could figure out how many degrees each one of these arcs represents. We're not going to do that right now, but you might see that in your work. And we rotated that number of degrees. Now we don't have to know the number of degrees to actually do it because these arcs are all equal. We noticed it was 3 movements from arc to arc, and we just spun each one. So this is our D sharp major chord. All right, and then the last example. So in the figure shown here, similar setup to what we did on the front. CA represents the direction that Kathy is facing. So again, we've got someone looking a certain direction. Kathy's dog Susie Q is running around Kathy in a counterclockwise direction, this way. Her field of vision is 140 degrees. So that's where this 70 is coming from. This is 70, this is 70 degrees. So altogether, that's 140 degrees. How much of a turn is necessary so that she can see when Susie Q is directly behind her? So they specifically tell you that it's running counterclockwise. So we're going to assume that with her eyes, she's going to follow it counterclockwise. So we're turning. So right now, when she's facing forward towards A, she can still see to B. And so we need to get B to turn all the way to S. So right now we know that this whole section here is 70. We know from A to S is 180. So we've already gone 70. The other piece is going to complete my 180 degrees. These two arcs together have to equal 180. So I'm just going to do 180 minus 70, which is going to equal 110. So I know that this is 110 degrees from B to S. And then you always need to consider your positives and your negatives. In this case, we're going counterclockwise. And so it would be 110 degrees positive